There's always this 30-second delay or so with Zoom connecting to YouTube. Okay, fabulous. Excellent. All right. Well, welcome back everybody for yet another lively session for the Monsoon Seminar Series. Today we are joined by our speaker, Parth Shah from the University of Haifa. And so Shah Parth is a PhD student at the Department of Marine Geosciences in the University of Haifa in Israel. His PhD work is aimed to develop comprehensive pictures of climate variability over the southern Arabian desert, specifically during the late Holocene. Currently, he's working on 2 lacustrine sites in Yemen for paleoclimatic reconstruction, but specifically and especially focusing on understanding the impact of climate change on the different components of the ecosystem. He received his BS and his MS in 2018 from the Indian Institute of Science Education Research in Mohali. And his MS dissertation work mainly focused on understanding the paleo-environmental changes in the Indian monsoon using inorganic and organic analyses from archives on the Indian subcontinent. He's received various scholarships and grants during his academic career, like the PBC Fellowship, the IAS Postgraduate Grant, and the Inspire Fellowship. And so without further ado, I would like to hand it over to our speaker. And if you have any questions for the speaker, please just type them into the chat and then we'll call you out at the end of the talk. And or you can raise your hand digitally and I'll call out onto you. So again, let's hand it over to Parth for his intriguing presentation about the Arabian Desert.
Thank you very much. Hello everyone, welcome to my monsoon seminar talk titled Late Holocene Monsoon Dynamics in the Southern Arabian Desert and their linkage to regional and global climatic drivers. In this presentation, I will be showcasing the part of my PhD work that I am doing at the University of Haifa, Israel. Sorry. Here are the contents of the talk. I have divided my talk into 5 parts where I will give a brief introduction on the research project that I'm working on. I will give generalized background information on the study area, followed by methods and proxies that I use for paleoclimatic reconstruction. Then I will discuss the results from 2 sites, Lake Al-Bizal and Lake Sarwan. Finally, I will summarize this study in form of conclusions. As we all know, that Holocene began around 11,700 years ago, after the last glacial period ended. The climate during the Holocene time interval is relatively stable and marked by warmer temperatures, which led to start of agriculture and the rise of human civilization. However, even within this relatively stable period, there have been various short climatic fluctuation driven by various natural factors like solar, volcanic, and ENSO variabilities. The early Holocene is marked by relatively warm intervals. However, the temperature drops around 8.2 thousand years ago, which is reported in major parts of the world. And then in this phase, between 6 to 7,000 years ago, the temperature reached its highest for the early Holocene, and that resulted in the increased precipitation around the world. During this period, we see different parts, lake records from around the world reported wetter phase. During mid-Holocene time intervals, we witnessed temperature dropping around 4,000 years. This interval is also very important and responsible for collapse of various civilizations due to drought conditions in tropics and subtropics. In general, the Holocene climate, the warmer phase during the Holocene climate mostly reflects the increased rainfall pattern, and this is well in line within the orbital monsoon hypothesis. Now, if we specifically focus on the past 2,000 years or last 2 millennia, which is marked by various short-term climate anomalies like Roman warming period, late antiquity, little ice age. However, medieval climate anomaly or medieval warming period that occurred around 1,000 to 1,200 years AD and little ice age that occurred around 1,500 to 1,800 AD are much more globally recognized. Studying the climate of past 2 millennia provides important insights into the impact of human activities on the Earth's ecosystem and help us distinguish natural climatic variability from the anthropogenic influence. Now, if we look at the famous hockey stick graph published by Manitel in 1999, it suggests the temperature change in the current warming period was much more higher than the medieval climate anomaly. And hence, this study of last two millennia can help us understand the cause and extent of these climatic patterns that we see in current timeline and help in projecting future climatic patterns. Here we see the data sets from around the world using PHIDA database, which help us understand the climate variability over last two millennia. And as we can see, the location of various sites around the world to estimate the global changes in the precipitation during past 2,000 years. However, if we look closely, most of the data points are more skewed towards higher and mid latitudes, with the limited data points from Sahara and Arabian Desert. Results from the simulations have provided that volcanic forcing is one of the major natural cause of climate change happening over last 2 millennia. However, there is need to add more data sets from climatic sensitive zones like Arabian Desert for better precision of this model to work. That brings me to the motivation of my research work. The climate of the Arabian Desert is not well documented during the late Holocene due to scarcity of continuous and well-dated terrestrial archives in the region. Here in the left side of the screen, you can see the location of various archives from the Arabian Desert, which mostly represents the Holocene archives. However, there are not many late Holocene records from this region. The other questions that we would like to explore is the what mechanism controls the position of ITCZ boundaries and its impact on the rainfall intensity in the region. Other questions involves how does globally recognized events like medieval climate anomaly, little ice age has affected the regional climate in the southern Arabian Desert. But in order to understand past climatic fluctuation, one should look at the modern climate patterns and more specifically modern precipitation data. The climate of Arabian Desert is characterized by extremely hot and dry condition, with the hyper-arid desert dominates the east and north of the Arabian Peninsula, while the southern part of Arabia is slightly more temperate due to the Arabian Sea proximity. Most of the seasonal precipitation in the over the southern Arabia occurs during month of spring, like March, April, and May, as you can see in the figure. And moreover, southern Arabia also receives rainfall during summer season during June, July, and August. However, the northern Arabia receives most of the rain during winter season of December, January, and February. Now, these modern precipitation data doesn't provide a comprehensive picture of climate change happening in the region. In this slide, you can see various extreme climatic events occurred over the years, from flooding to sandstorms to even snowstorms. This indicates there is a special inhomogeneity in the climate data system, limited availability of meteorological and paleo data set. If we specifically talk about Yemen, as mentioned in the earlier slide, that southern Arabia receives most of the precipitation during summer and spring, but in year 2020, the region received extreme precipitation that resulted during the winter season, and that resulted in an infestation of locusts and then led to food insecurity in the region. Now, if we look at the monsoon system that affects the climate of Arabian Desert, so Arabian Peninsula is situated between two monsoon systems, East African monsoon and Indian summer monsoon. During spring time, during March, April, and May, East African monsoon extends eastwards along the sub-Saharan region to over the Ethiopian highlands and takes moisture from Red Sea and precipitates over the western part of Yemen or western part of southern Arabia. During summer season, due to seasonal migration of northward migration of ITCZ boundary, the southern Arabian Desert receives moisture through ISM or Indian summer monsoon. Whereas during winter season, winter Mediterranean cyclone impacts the northern Arabian Desert and northeast monsoon impacts southeast Arabian Desert. That brings me to the research objective of my work. So the main objective is to increase the spatial coverage of paleo data set from this part of the world to understand the moisture source and delineate possible hydrological variabilities linked with changes in the monsoon systems. to understand the role of ITCZ and its impact on the regional climate. We would also like to test and develop various climate sensitive proxies like ostracods, biomarker chironomids that has not been applied in this part of the region for the paleoclimatic and paleoenvironmental changes. We would also like to study the various hydrodynamic factors that control the sources, transport mechanisms of the sediments, which are required to explore the paleoenvironmental changes. Coming to the site selection, as mentioned, there are not many records from Southern Arabian Desert, especially from Yemen. Hence, two different lake systems were selected for understanding the climatic fluctuation in the region. These lakes are situated very close to closed margin of modern ITCZ boundary. Hence, it can have a significant impact in the regional climate of the lake area. The first lake is a karstic lake, Al-Bizal, and the second lake that we have chosen is volcanic crater lake, Karif Sauron. Both lakes are from Yemen. The method generally is divided into two parts. First is the field work and then the laboratory analysis. The field work majorly involves the collection of short and long cores from different parts of the lake. We also collect various catchment and vegetation and water samples to understand the regional more modern settings, and that information can be transferred for understanding the past environmental changes. Lab work mainly includes description of cores, using visual inspection and identifying various lithological phases. Then we use various chemical, physical, and biological proxies to reconstruct past hydrological and past limnological parameters that can be linked with climate changes. We use multi-proxy approach to improve the reliability of these proxies. Chemical proxies majorly involves use of XRF, which is used for understanding the elements in lake sediments, XRD for the mineralogical analysis, TOC, TIC tells you about the total organic and inorganic content in lake sediments. Physical proxies like particle size or grain size analysis, magnetic susceptibility, and frictional porosity has been used in this study. Biological proxies mostly are like ostracods, chironomids, and lipid biomarkers are applied in this study. First, we look at the results from Lake Ghail al-Bazal. The Paleo Lake Ghail al-Bazal is located in the southern parts of Hadramaut province in Yemen. The geology of the region includes the Khabar group formation, which consists of metamorphic to enkimetamorphic units. The region is surrounded by sandstone, greyback, conglomerate, rhyolite, and quartzite rocks. The region is also characterized by various karstic sinkholes that are developed due to dissolution of gypsum and limestone. Lake Ghail al-Basal has been occupied in one of those sinkholes. If we talk about the lake level of this lake, which is reduced to a small residual pool due to human withdrawals for irrigation purposes. The hydrological balance of this lake is primarily controlled by summer precipitation that falls over main wadi, and the evaporation being the sole output. We retrieved 3 sediment cores from this particular lake, and based on initial visual inspection and sedimentary proxies, we generated a 3.3 meter composite core called GBW. Then we started working on it, and we applied various chemical, physical, and biological proxies. Initially, we started with non-destructive analysis like XRF for understanding the sources of sediments, like whether the sediments are coming from allopathanous or orthogonal sources. This in turn can reflect changes in the climatic and mineralogical conditions. We use proxies like titanium versus aluminum, potassium versus aluminum, and rubidium to estimate the detrital influx into the lake basin. We use calcium and sulfur ratio to estimate the orthogenic deposition of calcium precipitation in the lake environment. Based on the XRF analysis, we divided our core into 3 units. Unit 1 is marked by increased value of detrital elements like titanium, potassium, and rubidium. From the bottom, we can see lithological unit 2 mostly consists of increased abundance of orthogenic calcium and more sulfur in this region. Here, the preliminary result shows that unit 1 can be an indicator of wet phases, whereas unit 2 can be indicate arid environment. We use proxies like TOC and TIC to track changes in the organic matter deposition through sedimentary sequence. The TOC-TIC data indicates the unit 1 have higher values compared to unit 2, specifically for the intervals with higher data influx. TOC-TIC doesn't provide sources of organic matter, but can display an initial picture of productivity changes in response to climatic shifts. The organic matter in the lake can be derived from allogenic source like catchment runoff or wadi influx, or can be formed within the lake system. We also looked at the XRD data set, which revealed that Unit 1 consists of calcites and quartz. And Unit 2 is marked by presence of gypsum, which corroborates our initial hypothesis from the XRF data that the Unit 2 can be indicative of Arabian. We also looked at grain size distribution from GBW core. It is largely characterized by silt with minor variation of sand and clearly silt fractions. To distinguish the sources and the transport mechanism of sediments, we used n-member mixing approach. This approach applied on this core resulted in 5 distinct n-members that can be attributed to different transport mechanism. EM1 is the finest grain size that falls around clearly silt fraction. 7 phi values, and these can reflect fluvial or wadi influx into the lake basin. Hence, finer fractions like EM1 along with other proxies, XRF and TOC data can be interpreted as the unit 1 can be interpreted as increased precipitation in the region. EM2 mostly consists of medium to coarser silt and can reveals the aeolian input in the lake basin. EM3 is situated around fine sand fraction, which could have formed due to lowering of lake level, and that resulted in moving of shorelines. The greater abundance of EM2 and EM3 is attributed to a arid environment. The age model of GBW core is based on 5 radiocarbon ages applied on terrestrial wood, twigs, and plant remains. The radiocarbon ages are stratigraphically consistent and goes up to 900 years common era. The calibration of the dates were done using latest INTCAL 2020 curve calibration curve, and the age depth model was carried out using OxCal program. Based on the chemical and physical proxies, we determine various intervals with high and low precipitation regime. We see increased detrital influx, increased TOC values in unit 1, and deposition of finer sediments in the unit 1. Furthermore, the wet intervals in this particular unit can coincide with this particular event called medieval climate anomaly. Whereas unit 2, we see gypsum formation, increased aeolian influx, and higher precipitation of authentic calcium into the lake basin. These dry episodes in Unit 2 appears to prevail during Little Ice Age. The possible cause of MCA and LIA has been attributed to various natural as well as anthropogenic forces. But in this particular lake setting, the fluctuation in the regional climate during MCA is mostly attributed to the changes in the intensity of solar forcing. And thus, in this particular region, MCA is wet and LIA is dry. We also estimate that this anomaly could have been also triggered by northward migration of ITCZ in response to increased solar forcing. We compared our data sets with the other Holocene records around the lake region. We observed a similar precipitation trend in other sites from Northwest Arabia, from the lagoons we see, and also from East Africa, lake record from Kenya also suggests that the MCA is marked warm and wet, whereas LIA is dry and cold. Furthermore, marine records from Arabian Sea also reports increased monsoon activity from 700 to 1200 years common era, and weaker monsoon during 1300 to 1500 common era. However, in the marine record from Gulf of Aden, doesn't indicates any major substantial changes in the temperature change during MCA and LIA. However, we can, based on these regional comparison, we can suggest that MCA and LIA had a significant impact in the regions where it is impacted by Indian and East African monsoon routines. Now we try to estimate the impact of climate shift during MCA and LIA on lake ecosystem using bioindicators like lipid biomarkers, ostracods, and chironomids. But before applying this proxy for paleo-environmental reconstruction, we should first test their applicability for the first time in this particular region of Yemen. GBW core shows high resolution precipitation changes during past 1200 years based on chemical and physical proxies, and we have identified various wet and dry intervals. Wet intervals are marked by, in the left side of the figures are shown by blue blocks, and the dry intervals are shown by the orange blocks. Now we already have some idea about the climate change during this interval, which can help us understand how these bioindicators will respond to these changes. And additionally, how these bioindicators can also provide various information on the changes happening in the lake ecosystem, like changes in the water salinity, lake level, productivity, and oxygen content. So first we use biomarker analysis. We use leaf wax biomarker. We are primarily focused on alkanes in this particular study. Alkanes can be produced by terrestrial plant, aquatic plants, algae, bacteria, etc. And they are mostly preserved in the lipid fraction of the sediments. Terrestrial plant produces higher chain lengths from C27 to C33, whereas the aquatic plant produce mid chain lengths from C21 to C25, and bacteria and algae produce lower chain lengths in the lake basin. Hence, the relative abundance of different chain lengths can be used to disentangle the sources of organic matters, which can reflect various paleo-environmental shifts, such as changes in the aquatic productivity. We use two proxies called T aqueous and tar. The formulas are mentioned in the slide to estimate the sources of organic matter based on following these equation, as you can see. Higher P aqueous value indicates increased abundance of aquatic plants or increased primary productivity, whereas tar indicates increased contribution of organic matter from terrestrial plants in the lake. During MCA or wet intervals, we see higher P aqueous and tar values indicating increased primary productivity. This may be attributed to increased input of nutrients into the lake, which could have enhanced aquatic photosynthesis and in turn the primary productivity of the lake. Furthermore, the decrease in tar values during MCA can be linked to increased production of algae and bacterial sources of analkanes, the lower chain lengths. However, during the dry intervals of LIA or during 1400 to 1700 years, higher tar values and lower P aqueous values are being reported. The shift in alkanes can be linked with changes in shoreline, resulting in more terrestrial alkane sources and alkane source contribution in the lake basin. Hence, an alkane study help us understand the productivity change and help us understand the impact of climate change on the ecosystem. Then we use ostracod analysis. So basically, ostracods are small size arthropods, and their shells are made up of calcium carbonate. The distribution of ostracods can be influenced by climatic factors like temperature, precipitation, and other limnological factors like salinity, alkalinity, and conductivity of the host water. Generally, the higher terrestrial flux and or the increased organic matter production can boost ostracod population. This trend is observed during MCA or wet intervals. We see increased abundance of this particular species, B. lineata, in Unit 1. And this particular species is being reported, is being associated with the aquatic macrophytes. Furthermore, during LIA, we see the increased abundance of these two particular species called Western Mula and Limno-C3. And these are this ostracod species mostly thrive in more saline environment. Hence, ostracod investigation reveals that the MC intervals were more productive and less saline, whereas the LIA interval were more saline and less productive. Now we use chironomid analysis to estimate the impact of climate change on the ecosystem. Chironomid larvae are one of the most common aquatic invertebrates that are found in lakes and rivers. Some species of chironomids can live in sediments or in macrophytes. In semi-arid and arid region, the changes in the chironomid assemblage are dependent on the factors like water depth, salinity, lake productivity, or even oxygen content. Their head capsules are well preserved in lakes sediments through time, making them an excellent archive for reconstructing past climatic and environmental conditions. Low chironomid head counts appears during MCA in this particular core, whereas higher head counts abundance occurs during utilization. Higher abundance of chironomids can be linked to dry phase of LIA. This is because during the dry phase, there is less freshwater input, resulting into lower turbidity levels, and that can have resulted in more oxygen content in the lake basin. The dominance of this particular species, chironomy, in during MCA can be reflective of more productive and less oxygen content in the lake basin, whereas this particular species, Tantia serini, can be indicative of less productive and more oxygen content in this particular interval. We use de-trended corresponding analysis to explore the relationship between bioindicators and climate variables in the dataset. DC analysis provided three distinct zones that can be used to arrange bioindicators along the climate gradients. Zone 1 reflects close association of ostacot species like Bilineata and Piecos proxy. And we are seeing that they are more close associated with the wetter periods and better periods. This suggests that increased precipitation resulted in changes in the sources of analkans and presence of swimmer ostacot species. Zone 2 is marked by association of drier periods and with the increased abundance of chironomids and more contribution of organic matter from the terrestrial sources. Zone 3 is characterized by intervals with the mixture of wet and dry episodes, which are associated with these particular species, Fabio for miscondona, which can be controlled by multiple processes in the lake setting. Hence, the use of this bioindicator provides environmental changes happening during past 1200 years. To summarize these impact of ecosystem due to changes in the precipitation in Lake Ghail Al-Bizal during the MCA interval, where we have more input of fresh water through wadi influx that leads to more nutrients coming into the lake basin, resulting in more aquatic productivity. And due to higher lake levels, we see less saline conditions. Whereas during LIA, we see due to decreased freshwater input from wadi influx that results in decrease in lake level that leads to rise in salinity and dissolved oxygen content. Now we look at the results from Lake Karif Shauran from Yemen. The lake is situated in the close proximity to Gulf of Aden. The volcanic crater lake Karif Shauran has no inlets and has two minor outlets that can become active during high lake level stand. This lake can be an excellent archive for understanding paleoprecipitation changes. The walls of lakes are steep and is mainly composed of basaltic and olivine pyroxene-rich rocks. We retrieved two sediment cores from this lake, and based on visual inspection and initial sedimentary proxies, we generated 1 meter composite core. The lithology is majorly divided into 5 lithological units. We identified various volcanic ash layers, turbidites, and other units like alternation of organic and rich layers and evoprite layers. We also recognized various silty coating of aragnites. And based on the initial analysis, we withdraw that these 5 major units and the chronology of this core is mainly characterized by 3 radiocarbon dates on ostacot shells, and it goes up to 3,800 years Callier BP. The age model was generated using Bayesian statistics with the help of Bacon package offered by RStudio. We initially used physical proxies like magnetic susceptibility, density, and fractional porosity. to identify various volcanic ash layers. These layers are marked by increased MS values, increased density, and the lower fractional porosity values. The chemical proxies like XRF and TOC investigation was also done on this particular lake core. Here, calcium normalized counts are primarily controlled by bioacidic and oxygenic carbonate precipitation. We use iron and silica as a marker for volcanic ash layers. And furthermore, potassium versus titanium is used as a proxy for physical weathering. The TOC and TAC measurement reveals that during intervals with the higher values of physical weathering or increased value of potassium versus titanium, the TOC values are reported higher and TAC values are reduces. We also did XRD measurement that revealed four major mineral assemblages. Aragonite is precipitating in the lake during, there are four major minerals like calcite, aragonite, tridymite, and halite. Aragonite in this particular lake setting is precipitating during relatively low lake level stand, whereas halite represents the extreme low lake level condition. Tridymite is a silicon dioxide mineral which can be derived through weathering of volcanic rocks present in the catchment. Coming to the biological proxies, we use alkanes to understand the productivity changes in the lake. We disentangle the sources of organic matter based on alkane chain lengths. Here we used P-aqueous ratio to estimate the contribution of organic matter derived from aquatic versus terrestrial plants. Here the result shows that intervals of 60 to 90 centimeter P-aqueous values are reported higher due to higher abundance of aquatic plants. This can be indicative of low lake level stand, whereas the volcanic ash layers and turbidite intervals, we see lower values of P-aqueous indicating heterogeneous input of organic matter, indicating high lake level stand. Other biological proxies we used for paleoenvironmental and paleoecological changes is ostracods. We identified only one Euroholocene species called Cypredis torosa from this particular lake core. This particular species can reflect salinity of the lake water based on sieve pore morphology on the shells. So you can see the sieve pores in the particular slide, and during when the salinity increases, the ostracod sieve pore shapes changes from round to irregular. And if we count the sieve pores from each ostracods and use this particular equation that you can see in the slide, we can quantify the salinity of lake water in the past. The data, salinity data reconstructed using the sieve pore morphology data sets reveals that 60 to 90 centimeter intervals, we have seen more saline condition compared to the top of the morphological unit. Now, multi-proxy approach shows that during wet or higher lake level, we are witnessing higher physical weathering, lower MS values, and lower precipitation of evaporite formation. We are also marked by various intervals like higher heterogeneous input during the wet phases, whereas drier phases are more characterized by lower weathering, higher evaporite formation, and higher salinity. We related this high and low precipitation regime with various globally recognized events like Roman warming period, which occurs from 2000 to 600 years Callias BP. Late antiquity little ice age is also recognized in this particular core, which is here shows dry phase. Medieval climate anomaly and little ice age is shown also in this particular region or in this particular lake setting. MCA here is also wetter, as we have seen from the other lake from the Yemen, and little ice age is reported here drier. We link this regional climate of these particular data set with changes with the solar and volcanic forces. Coming to the paleoclimatic influence based on records from both sides, we identified various climate anomalies like little ice age, medieval climate anomaly, late antiquity little ice age, and Roman warming period in the region. We link these hydroclimatic changes to global climatic drivers like solar, volcanic, and insolvability. Initially, in the introduction slide, I mentioned that the climate of late Holocene is majorly controlled by volcanic forcing, But here, majorly, the hydroclimatic change is responsible with solar and ENSO variability. Hence, we draw two possible mechanisms that could have impacted the regional climate in the Southern Arabian Desert. The first is the role of ITCZ. Now, many study indicates the position of ITZ was more northwards in the Holocene time interval, as shown in this graph. There are two possible ITCZ proposed boundaries during Holocene. However, during mid-Holocene, this ITCZ gradually started to move more southward, resulting in decreasing Indian summer monsoon fronts. But we know that the changes in solar radiation can result in changes in the position of ITZ boundary, meaning if there is more north in the northern hemisphere, we are getting more solar forcing, then the ITCZ gradually can move more northwards. So this can be one of the reasons why we are getting more wet and dry climatic changes in this particular region. The other regional climatic drivers like Red Sea convergence zone can also impact the precipitation change in the Southern Arabian Desert. The RSCZ is a semi-permanent convergence zone that is generated due to difference in temperature in North and South Red Sea. RSCZ generates strong winds and currents which can flow from Red Sea to Southern Arabian Desert. During winter months, the RSCZ can intensify and shift more northward or southward, leading to increase in rainfall in the southern and northern part of Arabian Desert. Moreover, the recent studies have also shown that there is a close correlation between ENSO variability and these shift in RSCZ during El Nino phase. We are seeing more northward migration of RSCZ, which can impact the changes in the rainfall patterns in the Southern Arabian Desert. Coming to the conclusion, so this study provides comprehensive picture of continental scale climate variability as faced by changes in the intensity of monsoon during late Holocene. We try to increase the spatial coverage of paleo data set from this particular region. The multi-proxy investigation displays enhanced precipitation during MCA and Roman warming period, whereas arid condition is reported during Little Ice Age and late Antiquity Little Ice Age. The evolution of both lake basins are being controlled by various regional and global climatic factors, but majorly the driving factor is solar insolation changes or zonal shift in ITCZ. We tested and developed various climate sensitive proxy to estimate the impact of precipitation change on the lake ecosystem. Overall, this study can help us understand the role of ITZ with respect to monsoon dynamics. Moreover, it will help us develop various long-term strategies for seasonal prediction in Southern Arabia. The next step of this project is to measure compound-specific isotopes to delineate moisture source in the region. We are currently in measuring this isotope in Germany, and we are also planning to measure oxygen isotopes on ostracods. This can help us better understand the mechanism controlling the rainfall patterns in more precise way. With that note, I want to thank all of my collaborators from different institutes for their valuable input. Specific acknowledgement to my PhD supervisor, Professor Nicholas Waldman, Dr. Ilaria Masini for helping with the ostracod analysis, Dr. Anup Ambili for letting them use their biomarker facilities, Professor James Russell for providing access to this lake site, and my colleagues Sonia, Ankit, and Bulbul for helping for the data generation. We also acknowledge the various funding agencies that provided grants and fellowship to fund this project. With that note, I thank everyone for your kind attention, and any questions and suggestions are most welcome. Thank you.
Fantastic. Thank you for such a nice talk. So we'll give everybody a moment to put their questions into the chat. And while everybody comes up with their questions for the chat, I do have a quick question for you.
Sure.
So I guess Southern Arabia is not my area of expertise, but when I think of Southern Arabia, I think of a lot of the speleothems that are located around there. And I was curious if there were any of these speleothem records that went over the timescales that you were looking at, or if there's kind of like an absence of those And that kind of, again, further highlights kind of the importance of your types of records.
Actually, it's a great point that you brought. So there are some stalagmite records from, let's say, Yemen, from Socotra Island during this time phase. But the problem with them is they are not very continuous. There are gaps. So from mid Holocene to late Holocene. So there are there is a record from 4,000 to 3,000. Then there is a gap for 1,000. So it's like that. So there are some limitations. Other thing is there are no lake sediments from this particular region, specifically from Yemen side, because we all know what's going on in Yemen right now. It's very hard to take samples from them. Other thing is that there are some marine records, but marine records cannot always store various short-term anomalies, like because medieval climate anomaly is like very short. It happened only for 100 to 200 years, let's say, in global perspective. So marine record may or may not can preserve this thing. So hence, we choose to select these two sites or two lake records for the paleoclimatic reconstruction.
Yeah, well done. You have continuous high resolution records, which is exactly where you need them. So excellent.
Yeah.
Okay, great. I see there is a digital hand that is stuck up. And I think, if I recall, that might be Peter Clift.
Yeah,
Yes.
hi.
Okay.
I just wanted to ask a quick question. So in your first leg, you showed us these 3 units, and the second one was roughly the same age as the Little Ice Age, but you were showing the Little Ice Age as being a little bit younger, and I wondered why. Do you think, is that real, or is that just because of the uncertainties in your dating, or perhaps the Little Ice Age is a little bit older in Arabia compared to Europe? Is that a real difference, or is?
So you are mentioning, let's say, this graph?
Yeah, exactly, like that. You see, the Little Ice Age is a little bit younger.
It's younger.
In Unit 2, but yeah, it looks like it, doesn't it? The way your bracket on the right there.
Yeah.
And the pink shading begins before the Little Ice Age. Is that real, or is it just because your dating is not great, or the Little Ice Age is a different time in this part of the world?
So there is like in let's say South Asia, we see Little Ice Age from, let's say, little bit like, let's say, 1300 to 1500 AD, whereas in the East African zones, we see a Little Ice Age little bit in younger time intervals, like 1500 to 1800 AD. So basically, there are different places where we have seen like Little Ice Age has impacted in different like, let's say, short let's say I don't know. So sorry to yeah. So okay. So to understand these, maybe we can have the uncertainty in the dating method, but the general perception is the Little Ice Age throughout the world is between 1500 to 1800 AD. It can be up and down, depends on where you are in the planet. But based on the various regional record, we decided that maybe the Little Ice Age mostly is confined between 1500 to 1800. But we can see that the end phase after 1700 in this particular slide, we are not getting very dry interval. So I hope I tried to answer your question, Peter.
Thank you very much.
Yeah.
Okay.
I see there is another digital hand up, and I think that's Maya Matadi. Would you like to ask your question?
That's correct. Thank you very much. And thank you for the presentation. I was missing on the first lake, and basically also for the second lake, 2 aspects. Maybe you might want to expand more on them. One is the temperature effect on the salinity in this region. I think also the absolute temperatures, air temperatures, contribute a lot to the salinities, not only the inflow of the rivers or the contributors. And the other one is the role of dust, basically, as fertilizer. So it's not only the rivers bringing nutrients, but also the dust from the Sahara and from Africa, basically. Can you please expand more on those two mechanisms?
Okay, so thank you very much for your question. So first I'll answer the second question regarding the dust. So as you mentioned, dust can come from Africa, or let's say Arabian desert. But here we see the size of dust is very coarser, like it comes between medium to let's say coarser silt. Hence, we estimate the dust source is more close, is in more proximal zone. So it's coming from a very short distance. So the chances of getting nutrients from the dust is very small. However, we cannot neglect that. Regarding your second question regarding the temperature shift, definitely we don't have any temperature reconstruction based on the available data set. But as I mentioned, during the late Holocene, this part of the region, when there is a wet interval, it can be, and it also indicative of warm season. So it can be warm and wet, or cold and dry in this particular part of the region during late Holocene. So maybe by that we can say that medieval climate anomaly was warmer and little ice age was colder. However, like other proxies like GDGTs can provide more insights into water temperature, but currently we have not looked at it, but maybe in the future. Yeah. Thank you.
Thank you.
Any other questions? Please raise your hands or type into the chat. I have another quick question, actually. While people mull over other questions. So forgive me if I missed this, but in your second lake study, the Mar Lake, did you at any point have evidence for the overflow of this lake?
Yes, we do have, but like as I mentioned that there is actually seepage in the because this lake is actually more in altitude than the sea, the Gulf of Aden. So during the if I can, like, maybe I can show you the photo of the crater walls, and we can see based on the morphology of these let's say walls. You can see there was an like let's say overflooding of the lake water due to higher precipitation changes. And other things is also like we reconstructed the hydrological fluctuation using ArcGIS. Second, which indicates there are two major outlets from these particular zones. We estimate that during the high lake level, these two can be, the outlet can become activated.
Okay, thank you. Yeah, just because I know that this is kind of or at least a hot topic, and at least I know like planetary geosciences, you know, for kind of at least getting a baseline or even a maximum more or less for kind of precipitation variability when you get kind of these overflow periods. So I was just curious if that you had thought about it, and clearly you have. So yeah, cool. Are there any other questions from the audience for today? Oh, I see another digital hand up by, I think Mayar. Is that remaining up from before, or is that a new question?
No, there's a new one, and rather actually a comment than a question, or maybe a question. Yeah. On one of your latest slides, you show this ITCZ position. In one case, even north of the Arabian Peninsula.
Yeah. So
I'm having a hard time, and I think every atmospheric scientist would agree with me. ITCZ being that far north and kind of explaining it physically.
I agree with you. Like,
it's just maybe a rain band, or maybe just the outreaches or the reaches of a rain band, the northernmost reaches of the rain band. But putting ITCZ on that position means that basically north of it belongs also to the rain band and basically the tropics. And maybe we should really be distinctive what is ITCZ and what is just a rain band.
I totally agree with you that the ITCZ should not be that high. Let's say you are, I think, referring to this figure. Yeah. So there are two proposed ITCZ northernmost point. So one estimated by Friedman et al. In 2007, which I think should be the northernmost point of ITCZ boundary, because in the northern Arabian desert, we don't see much, let's say, wet intervals during, let's say, during medieval climate anomaly or like northern of Arabia. During the wetter phase, there are many wetter phase in during the late Holocene as well as the early Holocene time intervals. But these events are not reported in northern Arabia. So that can explain that ITCZ didn't move more towards the northern Arabian side. So like the ITCZ boundary proposed by Banner et al. In 2008, I think it's cannot be the case. More it should be in between the central part of Arabian Peninsula. So I agree with you.
Excellent. Okay, well, I think we've asked plenty of questions for our speaker for today and kind of combed his brain for some more information about his current work and some very exciting, what looks like future work out of these same two study areas. So I would ask everybody to put our hands, physical, whether or digital, together and thank our speaker, Shah, Parth, today for your excellent talk. And so before everybody runs away, I believe that we do have another talk next week as part of our seminar series. And so details will be sent out with that, of course, by email by one of the hosts. And I would like to wish everybody a good morning, good afternoon, good evening, wherever you are in the rest of the world. And thank you for attending. So thank you so much.
Thank you for the invite. Thank you very much.
All right. Bye, everybody.